Hello, everyone. My name is Esmaeil, and I'll be presenting our NeurIPS 2023 paper, Mixed Initiative Multi-Agent Apprenticeship Learning for Human Training of Multi-Robot Teams. This work was done during my PhD at Georgia Tech and along my collaborators, Jerry Xiong, Dr. Mariah Schrum, and Dr. Matthew Gombolay. The key question motivating my work here is that can we directly teach robots to coordinate and collaborate by showing them how to do it? And to answer this question, we propose learning multi-agent coordination and collaboration policies from expert human demonstrations. But why learning from demonstrations? In recent years, multi-agent reinforcement learning, or MA-LfD, has been predominantly used by researchers to optimize a reward signal for learning multi-robot tasks. But the success of RL heavily relies on sophisticated reward shaping. However, accurate and expressive reward shaping is very hard for humans to achieve, especially with increased domain complexity. Also, humans often have significant preferences in the way that they do things that robots may not be able to achieve or learn through reward shaping. So we decided that rather than having a human control an entire swarm of robots at once and tell them here's all the bits of information that you have to send to each other in a decentralized fashion so that you learn decentralized coordinated action and communication, what if we have the human just tell all the agents, here's what you should do, and the agents can then learn on their own how to communicate or what information they need to share with their neighbors in order to figure out which action is the best such that they can fulfill the request or objective of the human operator. And so in our proposed mixed initiative multi-agent apprenticeship learning or mixture, every agent have their own decentralized policy. We're going to have a data set DE of human samples, and we're going to train a discriminator that backprops through the networks so that the agents learn both the right action as well as the right messages, CIJ or ZJI, in order to trick the discriminator into not being able to differentiate between what the multi-agent system is doing or what the human demonstrator would have done controlling the robots. Important thing to notice here is that these ZIJ or ZJI messages are not being taught by the humans. They are being implicitly learned in a semi-supervised fashion to rationalize the underlying expert demonstrations without the need for an auxiliary reward or direct human data, offloading the challenge of doing that for the humans. For the sake of time, I won't go through the details of the mixture architecture here, but I'd be happy to answer any question at the poster session. But what I do want to point out is a mutual information maximization component reverse model that we add to our mixture architecture, in which we want to maximize the mutual information between the messages that are being sent and the observation-dependent actions robots are taking. The goal of the mutual information maximization in the reverse model is to improve the communication policy distribution for an agent given an observation by reducing the entropy in distribution over messages after observing a state or receiving a message, so that agents are more certain about taking an action after receiving a message. To answer our research questions, we did a user study in which we had real humans come and teach robots in a user interface called FAR Commander that we specifically developed for this purpose. FAR Commander is a publicly available heterogeneous multi-agent domain that requires communication between agents in order to successfully accomplish the multi-agent task. For our conditions, we're either going to allow for humans to demonstrate both communication and the actions that each agent should take, or humans only demonstrate the action that should be taken by the agents, and the robot team is going to reverse engineer what information they need to share with the teammates. We looked at a variety of metrics, both objective and subjective, from game score down to workload and usability. In a within-subject study design, we collected data from 55 subjects, all recruited from Georgia Tech students. We did this across 3 scenarios, easy, medium, and hard, growing the size of the environment as well as the number of agents and the initial number of fires. We observed that mixture significantly outperforms all baselines by reducing the number of steps required to successfully put out all the fires as a function of training iterations, and this is across all scenarios. So these agents are able to automatically learn from a relatively sparse signal of just the actions to take to reverse engineer what information they should be sharing with all their teammates without needing those labels from humans. And we believe this is the key point in mixture success. We found a number of positive results in terms of the total tasks completed, the average time per step that was needed by the human to teach the robots. So the total amount of time that the human needs to teach the robot team was reduced, and at the same time, the performance of the team is going up. And we also found subjectively that the users rated Mixture for having less workload and having higher system usability as compared to the system in which the users had to teach both how to act and how to communicate among teammates. Thank you for listening. And if you're interested in learning more about our work, please stop by our poster in the Great Hall, number 1504, or reach out directly. Thank you.